So the next speaker is Raymond Walters, and he will present to us UK Biobank GWAS result for 2,419 phenotypes.
Thank you. It's my pleasure to be here today on behalf of a large group of people in Ben Neale's group at Massachusetts General Hospital and the Broad Institute that has been working on this wonderful data resource that Jonathan just described out of UK Biobank, and in particular focusing on the kind of genome-wide association study effort and some kind of follow-on results from that. I'll say that kind of from the outset, as of when we initially put this together, it was 2,400 phenotypes. That number is, that clicker's not working. That number is now over 4,000. But the messages remain largely the same. So my hope in the time today will be to get through talking through just what that effort to compile those GWASs look like. So Jonathan's already walked through kind of the genetic data side of that in terms of measuring the genotypes in all these individuals in UK Biobank and imputing the non-measured variants based on these haplotype-based measures. And so we'll talk about what the rest of that process looks like for then trying to do the association between those variants and these over 4,000 phenotypes. We'll talk some about the efforts to share those results. We're talking, genome-wide results for those millions of loci by these 4,000 phenotypes and kind of what the most efficient ways are to kind of work with and explore that data. And then hopefully we'll have time to talk about some follow-up analyses that kind of build off of those core set of association results to look at questions related to things like heritability, so how much of the total variation in each of these phenotypes can we explain off of the observed genetic data, and starting to take advantage of the large scale of UK Biobank to be able to look at associations and subgroups. So in particular, taking the example of looking at GWAS specifically within males and females separately and seeing if we see signs of differences there that we may not have been powered previously to detect. So as was kind of already reviewed, UK Biobank is this prospective cohort of 500,000 individuals, and with this focus on kind of this later age band from ages 40 to 69. And because there was this invitation, it was by invitation, and because it was such a fairly intensive process, so you have to sit there at the touchscreen for an hour, you have to get your blood drawn, go through all these other measures. There is this somewhat tendency that the individuals in UK Biobank appear a little healthier than the average population. There's a great paper by Anna Fry and colleagues in PLOS, kind of doing the comparison of the demographics between this cohort and the UK as a whole in that age range. And even just evident here in terms of participant gender, you see the more kind of pro-social, perhaps, impacts of a larger female contingent to these cohorts. It's worth keeping in mind as we talk through the results that we see that this is not quite a random population sample, but it is among this kind of healthier group that has lower BMI than average, for example. They smoke less than is normal for the average UK population, things along those lines. I'm not going to go too long through the full list of phenotypes. Jonathan already summarized a fair amount, but I'll reiterate encouraging the data to showcase is an amazing resource just to get a better feel for the phenotypes that are available there. Everything from these kind of touchscreen measures, these various health measures, all these various things. For the results I'm talking about today, we specifically aren't looking at the couple of sets of phenotypes that require a little more expert processing, so especially the imaging phenotypes where you really need to handle, say, the brain imaging data in a specific way. And also the accelerometer data is similarly just a large scope of data that requires more specialized processing than, say, a suite of items that somebody answered on a touchscreen or a list of a person's diagnoses. And so within Ben Neale's group, kind of off of an application to use this data from UK Biobank, it's been a team effort to assemble these GWASs. Just due to the sheer magnitude of the data, both on the genetic side and on the phenotypic side. So this process really starts on the administrative side in terms of managing data access. and making sure we're doing a good job of just handling the magnitude of the data in terms of the many hundreds of gigabytes of data we need to process through for any given analysis. Software development to be able to make those analyses tractable. And then the work on the actual polishing of the phenotype data and running the GWAS themselves. So all the things I'm talking about today are the work of the many, many people shown here, among others. So on the phenotype side, we look at a few different things. The biggest chunk of these is taking the list of phenotypes basically exactly as they've been listed in the showcase from UK Biobank, and it is the way they're provided to researchers, and putting them through this workflow called Pheasant, which is published by Millard and colleagues, a group from Bristol, that tries to take essentially the reported values out of UK Biobank and come up with an automated workflow that gets you from this kind of raw data, raw in the sense of where UK Biobank has ended their processing of the data, to a clean numeric value that you can use as the left-hand side variable of your regression. So you're going to regress each of your SNPs against this phenotype, and so you need some clean numeric value to do that. And so the workflow that's kind of diagrammed out here, I realize the text is small, but the idea is just to give the overview of the shape, is so that you start with kind of the type of variable as it's been defined in UK Biobank. So you have your continuous variables, you have values that were reported as some integer value, and then you have categorical variables where either you could respond to just one category out of a list, or you could respond with checking off multiple categories on a list. And so the flow through here is essentially to take that raw input and process down to things that might work well in a regression. So for categorical variables especially, often turning them into either some ordered phenotype if there's a natural ordering to the options, or turning them into a set of discrete binary things. So there are, for example, questions in UK Biobank about, here is a list of disorders, tell us which ones you've ever been told by a doctor that you've been diagnosed with. And so you can turn that into separate items of were you diagnosed with high blood pressure, were you diagnosed with diabetes, etc. And similarly with the other things here, and perhaps on like the continuous and integer phenotype side, taking things where it's an integer value, but maybe there's only 2 or 3 response values that are ever given based on whatever the question is. And so maybe you want to turn that back into a binary variable instead. And so the idea here is not that this is the cleanest way to handle any of these individual phenotypes. We expect that there's a lot of rough edges here. It involves a lot of kind of curating at least an initial list of how the thousands of variables in UK Biobank have been encoded, but at least gives you a quick way to get through these variables efficiently, to do kind of a rough look at the phenotypes and get an idea of the association. So really that's a theme of the analyses I'm talking about today, is being able to get through the rough version of the analysis and finding that in the scope of UK Biobank, we can learn interesting things from there, and perhaps that this gives us a quick initial result that then allows us to prioritize follow-up of things. So about 3,000 of the phenotypes come from this workflow in Pheasant off of this encoding the variables. There's a separate set of variables that are pulled out that are ICD-10 diagnostic codes that we've summarized at the 2-digit level, because again, this gives us a nice uniform rule that we can apply across processing, kind of a raw list of each individual's ICD codes that maintains a balance between the specificity of the ICD code in terms of defining a diagnosis versus maintaining sufficient sample size to have enough individuals within category to say something meaningful. This is probably actually fairly fine-grained relative to the number of individuals in a number of these ICD codes. So given that UK Biobank is a healthier than average cohort, given that many ICD codes correspond to fairly rare phenotypes, many of these ICD codes end up having relatively small case counts, even in the full scope of UK Biobank. This list of 633 is after restricting to only codes where we see at least 100 cases out of the GWAS subsample for the cohort. But certainly you could imagine going much stricter and you drop additional phenotypes off this list. And then kind of the third effort that rounds out the 4,000, though there's some redundancy, so these numbers don't actually add up to that 4,100 number, is an additional set of endpoints that are also based on ICD codes, but have been a little more heavily curated to match some endpoints that have been curated within the FinGen consortium, which is another big biobank effort out of Finland, that have taken kind of heroic effort of working through their ICD code data out of their health registry and trying to summarize those ICD codes into more informative endpoints in terms of collapsing ICD codes that are often not clearly distinguished from each other in terms of how they're showing up in the clinical records, and things like that to improve power and interpretability of those kind of results. So for purposes of matching between their results and the results in UK Biobank, we've also run those set of endpoints. On the genetic data side, we restrict down to those individuals of European ancestry that Jonathan described as being evident on the PCA plot. So we define this entirely based on their apparent genetic ancestry rather than the self-report. This leaves us with a group of about 360,000 individuals, once you also remove individuals who are related to each other to avoid confounding in terms of correlated error between the individuals in terms of doing the regression. This is a slightly broader set than some metrics have focused on just the more homogeneous group who self-reported being white and British within the UK Biobank. So the main distinguishing factor here is including people who, for example, self-reports as being Irish rather than British. But it's still fairly restrictive in terms of the scope of apparent genetic ancestry. Even to across continental Europe, let alone to across the full global diversity of the UK. And for people who like QC of variants, there's also some variant QC that kind of moves from the full list of variants that Jonathan and the team from the UK Biobank release have assembled as trying to impute, and focusing on the ones that we think are common enough to have the statistical power to find associations between a specific genetic locus and a specific phenotype. Where once things are sufficiently rare, just the numbers are against you in terms of being able to find that association, and where that imputation process is confident enough as far as defining what the variation is like at that locus. So in some cases, either because it's rare or just because it's less clear from the haplotype structure, from the imputation, there are some places where it's just harder to identify those loci, and so we exclude those from the analysis as well. So that leaves us with a set of about 13.5 million locations across the genome to look at associations with each of these phenotypes. And so having assembled the genetic data and the phenotypic data, the kind of goal that remains is to go through and do that association. So this is a regression for each phenotype for each SNP. And for our purposes, we stick to simple linear regression, and this applies for the binary phenotypes, this applies for all the categorical phenotypes, and the reason is for pure computational efficiency. So in work led by Cotton Seed and implemented by Liam Abbott, who are pictured there at the top, have worked as part of building a more general platform called Hail, which is an open source genetics computational framework that make use of big data computing in the cloud. Assembled a framework that allowed us to get through the initial batch of 2,400 phenotypes in about 1 day's worth of compute. The full process from the release of the data from UK Biobank to us having results was probably on the order of a couple weeks, maybe a month in the first release, a little longer in the second round that got us up to the 4,000 phenotype mark. But really was enabled by this computational effort and focusing on, again, this kind of rough first pass analysis by sticking to just a plain linear regression. And we do throw in kind of important covariates in terms of those ancestry principal components to try and control for associations that are due to population structure rather than due to actual genetic causality, as well as things like age and sex that we know have broad effects on these phenotypes and so are useful to control for in terms of improving the power of these analyses and, again, avoiding confounding. And so once we've gotten through that compute, we do some post-GWAS QC to, again, reassess, make sure that we're looking only at the results that make sense, particularly for those rare phenotypes, kind of the combination of a rare binary phenotype and a rare variant, and our kind of rough approach of using just a linear regression leads to lots of statistical artifacts and uncertainty for those rare variants, and so some harsher filters are applied there. And we also do some sanity checks in terms of comparing the results we find in UK Biobank to previously published results for many of these phenotypes from other previous GWASs. And as Jonathan already showed with height, and it exists for many of these other phenotypes, we do see nice consistent results that give us some reassurance that even with the rough approach we've taken here, with the kind of automated processing of the phenotypes, the kind of rough linear regression, we're getting things that look consistent. And even things that are also consistent with the fact that we know the phenotypes are a little rough. So for example, we take the item in UK Biobank that is self-report of irritable bowel disease that clinically is kind of a combination of Crohn's disease and ulcerative colitis, which have somewhat distinct genetic mechanisms. We can see that that combined self-report item shows evidence of being a mix of the genetic loci we would expect for those two separate genetic etiologies. So we see things that, at least in places where we have prior information, where we have a little more trust in what we're seeing out of the GWAS. And so at the end of the day, we have lots and lots of Manhattan plots, which are, as we showed here. So again, those 19.5 million loci we've looked at across the genome and our degree of evidence for association with each phenotypes. And so we can look at not only the kind of things that if we were looking at a single phenotype, we might have picked out as a thing of interest. So BMI and blood pressure and diabetes and cancer and all of those things. But also, because we've been able to crank these efficiently, we can also look at things that maybe wouldn't have been people's top priority. So we can look at, the amount of time you say you spend outdoors in the winter, or how hot you like to drink your tea or coffee, and find that even for things like this, we're often finding strong evidence of genetic association. So again, distance clearly above our kind of threshold here for being interested in those results at many locations across the genome. And so kind of armed with those set of results, we've then thought about how to share those results and how to follow up on those results in terms of secondary analyses. So in terms of sharing the results, we've made a strong effort to having put in the work to compute all these results. So it is a day worth of compute, but it is a fair amount of time and effort from the group to get those through. We've pushed those results all public. So they live in a Dropbox that is graciously funded by Massachusetts General Hospital and is publicly accessible via download links and have been documented as a blog post. So we did the initial release of this in September 2017. With the initial list of 2,400 phenotypes, and we pushed out the kind of next wave that bumped us past 4,000 phenotypes in August. And also, as well as putting those results out publicly, also wrote up these descriptions of kind of our process ahead of actually getting through the process of publishing on, even through the scientific literature, and made all the code available on GitHub for how we had processed these analyses in HALE. But so that's kind of a big data dump to put on people, and certainly researchers were let us know that they were happy that we made those results available. But we also, there was an effort to how can you encourage people to look at that data, make it more tractable, and just other than saying here's many gigabytes of thousands of phenotypes, have fun. And so one of those efforts, led by another postdoc in the group, Andrea Gana, was to simply set up a Twitter account that set out one of these plots a day. So today's, you can find it on Twitter, is on work and job satisfaction. Is not a phenotype that finds anything, but it's there one a day with a link to where you can get the copy of the data and where you can into the place in the showcase where you can see the definition for this phenotype, what the actual question was asked, how the variable was coded, all those kind of things. And we found that this has actually been useful for encouraging public discussion. So I showed you just a moment ago that GWAS of how hot you like your beverage, and this prompted at least some interest from some people on Twitter. And so within less than 24 hours, there was a response from Abdel Abdouali, who's a researcher in the Netherlands, doing his own follow-up, taking those GWAS results and looking for relationship to other phenotypes and other enrichments, and kind of some heritability results that we're also going to be talking about in a moment, and trying to look at, well, so is are the genetic signals that we're seeing in this related to these other phenotypes? I found that kind of strikingly, it didn't seem to relate to many other behavioral phenotypes at least, but there was strong evidence that whatever was going on genetically there is perhaps involves some degree of enrichment in signal coming out of brain expressed genes. So again, a phenotype that probably would not have been on the top of anybody's list to look at out of UK Biobank, but prompting interesting science by way of getting these results into people's hands. Similarly, Eric Fahman, who is kind of shows up regularly and kind of thinking through these results on almost a daily basis. But so one recent example there was looking at the GWAS results for number of self-reported cancers. So this is a simple question of how many types of cancer you report having been diagnosed with over your lifetime. And so going through the list of associations found in that GWAS and comparing them to associations reported for specific cancers, and finding that by and large these each of these loci that are showing up as reported as being related to your total number of cancers are more strongly associated with some specific cancer, and kind of just tabulating what those list of cancers are here, kind of on a locus by locus basis. So for example, things that are more strongly associated with skin cancer or breast cancer, or other specific cancers that are showing up in this kind of combined phenotype, similar to what I described previously in the results for irritable bowel disease. And as Jonathan already covered, there's also work on browsers. So actually through that same PheWeb and Oxford Big Browser, you can also see, I think, at least the first wave of these GWAS results included there. So this is something we didn't get around to doing within the Neale Lab ourselves in terms of providing a browser. We just provided the raw release. But by making those available and making it publicly accessible and saying have fun, enabled other people kind of advancing on making it, again, better interaction with those results and being able to look at things such as that comparison across different phenotypes for a given locus. So for example, taking the top locus here out of association with BMI, this well-known FTO locus, and looking across the spectrum of phenotypes in UK Biobank and seeing that even for something quite as removed as whether your father had diabetes as an indicator that, you're genetically related to your father. So, if your weight's high, maybe your father's weight was high, and maybe that related to diabetes. The strength of the association is strong enough to even percolate through that degree of removal in the phenotype. And so really just another example of the different kind of things you can get at in getting more eyes on the data, more hands on the data from having produced this kind of scope of the data at a UK Biobank and working to explore that. So that's all focused on the GWAS results themselves, but one of the other things we can ask out of, say, those big Manhattan plots looking at each of the loci is what's more the total amount of signal there. So we have however many loci we think are likely associated with the phenotype across the genome, but how much in total is the genetics contributing? And this is, of course, kind of a classic quantity of heritability that exists dating back through the twin and family literature, back to, say, Galton in his regression of children's height on their parents' height. But in the kind of more GWAS context here allows us to look at, so of the set of variants that we've been able to look at in this form of study and looking at the genetic data and those genetic associations, what's our guess as far as how much those genetic variants are contributing to the different phenotypes? And this gives us a few different benefits. One is just to prioritize, so we have those 4,000 phenotypes, which are the ones that look like they have stronger genetic signals versus which are ones that are either noisy or not terribly heritable, or for whatever reasons maybe aren't necessarily the top thing to prioritize in terms of looking at genetics. There's also, at least for the method I'll talk about here, a kind of side effect that in estimating the heritability, we also get a look at how confounded the results are. So kind of distinguishing between what of the signals we see in these genetic associations look like we'd expect for genetic associations versus look like they might be driven by population structure or other sources of confounding. And so particularly this method of LD square regression, being able to get at that kind of look at our results as well. And kind of in the flip side allows us to use having so many phenotypes to look at to then reassess our methods. So how does this LD score regression method and other methods behave when we're looking at this many phenotypes? Can we see trends in how it behaves when we're looking across 4,000 analyses using the same method? And so this LD score regression method comes from this pair of papers in 2015, led by Brennan Bulick-Sullivan and Hilary Finucane. That essentially takes the idea that if we look at the signal in our GWAS and think about the amount of correlation that exists amongst neighboring variants in the genome, so this relates very strongly to that haplotype structure that Jonathan described that allows us to do imputation. But there's this local correlation structure among variants that are near each other in the genome. And so if you're at a spot in the genome where you are correlated with more variants around you, so for whatever reason you're on this haplotype that is more stable and you as an individual variant in the genome are tagging more general variation in your region, then we'd expect that kind of if we're in a model where, at least in the broad sense, we've distributed genetic effects broadly across the genome, there's lots of things having an effect, they're fairly widespread in at least some pseudo-random sense, then how many things, then the number of variants that a particular variant tags around them, that strength of their correlation around them, should then track with how much genetic signal it tags, because you have tagged a larger proportion of your region, and thus are more likely to be correlated with something that is causal for a phenotype. And so that gives us this fairly simplified regression form that we're taking the strength of the evidence in a GWAS and regressing it against what are called LD scores, which is this score of how correlated the variant is with the things around it. And it turns out that under a fairly simple model, the strength of this relationship is governed by the amount of heritability for the phenotype. And so this allows us to take those GWAS results and look at estimating this question of how much genetic variation relates to the effects coming off the genetics versus other sources of variation, whether it's the genetics we haven't looked at or whether it's environmental effects. And so this is another analysis that runs quickly. There's kind of a series of papers that I won't dive into deep to as far as the methods, but again, an effort to make the code available for it on GitHub. So both the underlying LD score regression code is available on GitHub, as well as the actual code used to run this analysis of the UK Biobank phenotypes. There's a lot of kind of caveats around those analyses that mostly have to do with how to interpret heritability. And so there's a lot of model assumptions involved, and we are working on heritability of those kind of automatically cleaned phenotypes. And there's that point I flagged at the beginning, that whether we're talking about a representative population sample or if this is heritability within this kind of self-selected group that's agreed to participate in UK Biobank. But those caveats aside, we find that across the thousands of UK Biobank phenotypes we've looked at, that almost everything shows at least some evidence of heritability. So on average, we see a SNP heritability somewhere in the 0.1 range, which is consistent with many other things in the literature, and there's a nice long tail of things where it goes much higher, so especially in terms of anthropometric measures, so weight and height and things like that, more in, say, the 0.3 range. And for roughly 700 of these phenotypes, once you account for multiple testing correction and do some filtering in terms of our trust in the kind of reliability of LD score regression based on the behavior of the method we're seeing. So that's the split here, that we have a high, medium, and low confidence group of those analyses, not based on the strength of association with heritability, just in terms of our expectation based on, say, the available sample size and things like that. And we find that there's strong enrichment kind of across the board, that there's signs of heritability kind of in the classic Eric Terpkheimer sense, that all behavioral phenotypes are heritable, that, well, at least by and large, there's not much where we could confidently rule out heritability. And of the things that are well-powered, the select group of about 1,100 phenotypes here, something like 80% of them are hitting at least a nominally significant p-value. And so I mentioned that this also gives us a look at confounding, and so we do indeed find that there's probably a little bit of confounding still present in our analysis, which is kind of consistent with various other evidence as far as residual population stratification and such. But kind of on the suggestion that this is on the order of maybe 5 or 10% of the signal we see in a GWAS is perhaps confounded, as opposed to the rest being kind of the polygenic signal we expect. And that we see better evidence for this kind of fit once we account for various annotations across the genome, rather than assuming kind of uniform distribution of the signal. And we learned some nice things from these results. We see that in the automated phenotype processing for continuous phenotypes, we have the choice of whether to keep the continuous value as given or to rank normalize. And we see that at least on average, we see slightly stronger heritability results if we take the version that was ranked normalized. We're able to, in terms of assessing the method, get a better feel of what the power properties are statistically. So this is a method that relies on bootstrap standard errors and doesn't have an analytic closed form for what we'd expect the power to be. But now, since we have 4,000 analyses of real phenotypes at a UK Biobank, we can start characterizing more empirically what those look like. And as kind of alluded to before, identify like specific subsets of traits where this method might perform poorly. And like everything else I've described, again, the effort to make that public, and so have, there's a browser publicly available with the first wave of results for 2400. We're working on updating for the set of 4000. That includes the ability to browse, the ability to look at some of these diagnostic plots that show interesting things in terms of trends of sample size and such, and also a downloadable set of the full results file. And it's similar to the GWAS bot on Twitter, have seen very solid signs of public engagement in terms of both initial release and kind of ongoing, as people visiting the site, people contacting us, and interesting heat maps in terms of across the globe that kind of correspond to probably people coming from various research centers, but having the chance to look at these results. So again, that effort to get in more people's hands. And so kind of the next thing we're thinking about is where this leaves us, is this gives us room to help prioritize phenotypes. So in the first round, we had 350 phenotypes with significant heritability after Bonferroni correction. And so that was a natural set to follow up on. And we'll extend that to the closer to 700 set that we're now working with out of 4,000 phenotypes. And gives us places where maybe we want to spend the additional compute to do something like a linear mixed model that would improve power, where we might want to revisit the phenotype definition and more carefully curate something for those phenotypes. And also where we can start building off of that core set of heritable phenotypes to look at how they relate to one another, and to how they relate in subsets of the data. I think looking at the time, I won't have a chance to get to the sex stratified results.
Oops, no more than 2 more minutes.
Yeah, exactly. So I'll just say that kind of the punchline there is that essentially that we do indeed have power to look at those results. So I'll skip over that section and find that, for example, this is a phenotype of facial aging, where if we do a test of, instead of looking at is a variant associated with that phenotype, we look at whether the association we see for that variant in men and in women is different. And so the spatial aging item is a simple question of, do people say you look younger or older than you actually are? And the variants we see that behave differently are very strongly variants that are related to male pattern baldness. And so it's kind of a good first proof of principle that indeed, like, it's not the most exciting thing. Like, you think about what that phenotype is fairly cryptic, and that it would make sense that the impact of balding matters differently in men and women. But that because of the magnitude of the data in UK Biobank, we now have the power to look at these kind of subgroup analyses and actually find fairly convincing evidence for differences along these lines. And so, yeah, so just to wrap up, so hopefully convince you that UK Biobank and efforts of this size in general have enormous potential to look at not only kind of the power of the genetic results, but also the scope of the phenotypic results that we've been able to process through, and that we've seen clear benefits of our efforts to get that data in the hands of more people quickly, to be able to look at data when it's being produced at that scale, not only in our group, but with the many other researchers who are working on UK UK Biobank analyses as well. And so in our own heritability analyses, we see that they're kind of across this broad swath of phenotypes, of the 4,000 we've looked at, especially out of the 1,100 ones where we see good statistical power, that by and large there is a genetic component, perhaps small, but at least some sign of a genetic component for those phenotypes to accompany the range of kind of environmental characteristics, and that we're excited to now have the power to start digging into as well these associations that are in subgroups. So thanks again to the many, many people in Ben Neale's group and our collaborators who have worked on this, and of course UK Biobank who made this possible by producing this wonderful resource. I'll leave it there for questions.
Thanks a lot.